Crude oil, the oil, that black oil that petroleum companies pump out of the ground, is really the remains of ancient forests. This black oil is the remains of ancient forests. If you think about what happens to leaves when they die in forests, they sort of turn this brown color. And the brown has a lot to do with the color of carbon. Carbon tends to form a dark color when it's all by itself. It's the black in the smoke of fires. It's the black in charcoal. It's the black in the sort of pencil lead that you have, the dark color of that. That's the color of solid carbon. As plants grow, they take the carbon dioxide in the atmosphere and turn it into their leaves and wood and stems. And so they accumulate a whole bunch of carbon. Now they create other molecules that are different colors, things like chlorophyll that make the leaves green. But when the plant dies, or when the leaves die, the other molecules, the pigments, decompose, and you're really kind of just left with the carbon. And so it turns this sort of dark brown or blackish color. It's the carbon that builds up in sand that makes sand turn into soil. If you think about the difference between beach sand, which is so light colored, and topsoil that you use for farming, it's that the topsoil has a lot of these decomposed organic matter, this decomposed carbon molecules that are sticking, mixed in with the otherwise white grains of sand. Sand is quartz, which is silicon dioxide. And it's the same sand, whether it's in beach sand or in topsoil. It's just in addition to the silicon dioxide, in topsoil you have a whole bunch of carbon compounds. That's making that black. Now imagine what happens over the course of thousands of millions of years, where leaves fall, a carpet of leaves fall in a forest every year, in the hundreds of thousands, in thick, thick sheets, and those gradually become broken down, and they darken the soil. And then when the rain falls and it scrapes tiny pieces of rock off of mountains and carries those pieces down into valleys, the rain, by scraping off pieces of mountains, buries these forest floors. And so you have all of this carbon that plants have made, and that is accumulated in their dead leaves and dead wood and dead plant matter. And it gets buried by the rain, basically. It gets buried by rainwater that scrapes apart mountains. The rain dissolves mountains little by little, but surely enough. The Appalachian Mountains nowadays, which are just kind of like rolling hills, used to be higher than the Himalayan mountains. They would have dwarfed Mount Everest. But over the course of millions of years, rain has scraped them away, and the tiny, tiny particles of rock that the rain has scraped off of them has become soils and sands in other places. For example, the soils in North Florida are mostly soils that came from rain scraping apart the Appalachian Mountains. So far, what we've established is that this plant matter has a lot of carbon in it, and so it creates this dark color, and over time it gets buried. Now, it gets buried deep underground, and the more time passes, the more sands accumulate on top of it, and the further underground it becomes. And as it gets compressed underground, that dark color, those carbons, turn into the black crude oil that people drill into the ground to find. What they're really doing is they're drilling to ancient forest floors where hundreds of thousands of ancient leaves and the trunks and barks of leaves, of plants, have all decomposed over time, and so you just have these gigantic stores of carbon molecules that those plants made, and that's what crude oil is. Now think of how many different carbon molecules ancient forests could have made over their history. You have some carbon molecules that are really small that they made. You have some molecules that are medium-sized that they made, and you have some molecules that are gigantic that they made. So, each of those have different physical properties. The small carbon as carbon chains get longer, they get stickier and more solid. The small carbon chains that the plants made and that is stuck in this crude oil, those are gases, things like the propane that you burn in a gas grill. The longer carbon chains, the sort of medium-sized carbon chains that plants would have made, those are liquids. Those are the types of liquids that are in gasoline. And the long carbon chains, those are more sticky. So you notice as the carbon chains get longer, they get stickier. So you go from gas to liquid. And the bottom there turns into something close to a solid. You'd have tars. That's what they use to make roads. So the next time you drive over a road, think you're driving over the remains of an ancient forest. And then as the carbon chains get even longer, you get hard things like coal, so solids. Now, sometimes the smaller chains are more useful. They're more useful for people and therefore more valuable to companies. So these liquids like gasoline are more useful and valuable than these longer carbon chains like the tars. And so people wanted to find a way to take this relatively inexpensive or not very valuable tar and break those long carbon chains up so that you'd get these more valuable liquids like gasoline or propane if you want to really break them up into small pieces. And the process that they determined to do that is called cracking. It's really important in the petrochemical industry. So what they do is that we'll treat this as a relatively long carbon chain. So that would be like a tar. Now technically this isn't quite long enough to be a tar, but we'll set that aside. We have a relatively long carbon chain. And in different processes, companies will use, or scientists will use, different catalysts to create a radical on the carbon chain. A really important principle to remember from this chapter is that you can only do two reactions with these alkanes. You can light them on fire and burn them. That gives you carbon dioxide and energy. So it's useful if you're trying to get energy, but not if you're trying to make a new compound. So you can light them on fire, or you can do radical reactions with them. Because by themselves, they're not especially reactive. You have to react them with something that's really reactive in order to make them react at all. And actually, as we'll see in the next exercise, even fire itself is a radical reaction. So scientists use different catalysts. Metal catalysts, they're complicated and kind of outside of the scope of this class. But those catalysts create a radical on these carbon chains. So you see this unpaired electron here. And once you have that radical there, you could understand how, through a radical process, the molecule can start to break or crack apart. It does that because by breaking a sigma bond, a neighboring sigma bond, this radical contributes itself to form a pi bond, and that steals a radical, one electron, an unpaired electron, from a sigma bond next door. There are two electrons in this bond. If one of them is leaving, the other one goes in the opposite direction and goes onto a new carbon. So if we number this, just to keep track of things, of what's happening, we have 1, 2, 3, 4, 5, 6, 7, 8. So notice that we'll have 3 carbons, 6, 7, and 8. Between 7 and 8 is just the single bond, but between 6 and 7 we've just created a pi bond. So that will be the pi bond that we form from those two radicals coming together. Then we're going to break the bond between 5 and 6, and these other 5 carbons will be separate, and the one lone electron that left that sigma bond will be a new radical on the 5th carbon. Now notice the effect of this reaction. We take a long carbon chain and we make smaller carbon chains from it. You crack it into smaller carbon chains. In other words, you take a long, sticky hydrocarbon chain and you crack it apart. So it's less sticky, less solid, becomes liquids like gasoline. If you keep cracking it, it would turn into gases like propane. And you could see, we'll draw that process just one more time. You could see how this could crack into even smaller pieces. Through the same idea, this radical contributes one electron. One electron comes from the sigma bond next door. The other electron in the sigma bond goes on to carbon, in this case, carbon number 3. So now we would have these two carbons, carbons 4 and 5, and we formed a pi bond between them. Then we broke the bond between carbons 3 and 4, so the first 3 carbons will be separated from it. And we formed a new radical on carbon number 3. So you could see how the process could continue and you crack the new radical into even smaller molecules. So you can start with these big long chains, which are really sticky things that tend to be a little less valuable, like tar. And through this radical reaction, they can start to crack and break up into smaller carbon chains. And the smaller they get, the more liquidy they become, and then eventually they become gases. So here, for example, you can see that we have ethylene or ethene that we used in the previous video, that acts as a plant hormone to ripen fruit, and that you can make plastics out of. So in this exercise, we've seen how you can use these radical reactions to crack long hydrocarbon chains into smaller ones. And the smaller ones are sometimes industrially more useful.